students. This is lecture number 11 on the series Linear Programming. The title of today's lecture is the Revised Simplex Method. Now, till now we have studied the simplex method, which is used for solving a generalized linear programming problem. Today we will see a shorter version of this simplex method, the objective being that this revised simplex method can be easily implemented on the computer so that it requires lesser computational efforts, lesser computational memory, and also it requires some constants which are called as the simplex multipliers, and we will see what are the advantages of these simplex multipliers. So, let us look at the outline of today's talk. First of all, the revised simplex method. Then we will take an example to understand the working procedure of the revised simplex method. During this, we will also see the simplex multipliers. What is the meaning of simplex multipliers? How they are obtained and how they are useful. And then we will look at the overall advantages of the revised simplex method. In the end, I will give you an exercise to solve. So, if you recall, in the simplex method lecture, we had solved this particular problem. Now, particularly I am taking this problem so that you can make a comparison between what we did using the simplex procedure and what we are going to do using the revised simplex procedure. So, the problem is the same, that is maximization of z is equal to minus 3x1 plus x2 plus x3. Now, this is a maximization problem, this is a minimization problem, and we need to convert it into a maximization problem when we are going to solve it using the simplex procedure. So, the objective function is minimization of z is equal to minus 3x1 plus x2 plus x3 subject to the three constraints that we have: x1 minus 2x2 plus x3 less than or equal to 11. The second constraint is minus 4x1 plus x2 plus 2x3 greater than or equal to 3, and the third constraint is twice x1 minus x3 is equal to minus 1. All the xi's from 1 to up to 3, they are all greater than or equal to 0. Now, this is the most general linear programming problem in which there is one inequality of the less than equal to type, one equality of the greater than or equal to type, and the third constraint is equality type. So, as before, the first thing we need to do is we need to convert it into the LP in the standard form. So, for this we need the objective function in the maximization form, that is maximization of 3x1 minus x2 minus x3, and this is subject to x1 minus twice x1 plus x3 plus x4 is equal to 11. Now, as you can see, x4 is a slack variable because we need to convert the less than equal to inequality into a equality. Now, in the second constraint is of the greater than or equal to type. So, we need to subtract a surplus variable, and the surplus variable is nothing but x5. So, the constraint becomes minus 4x1 plus x2 plus 2x3 minus x5 is equal to 3, and the third constraint that is given to us is having the right hand side as negative, but since we want that the right hand side should be positive. So, we have to multiply the entire equation with the negative sign, and we get minus 2 x 1 plus x 3 is equal to 1. All the xi's from 1 to up to 5 are greater than or equal to 0. Now, let us suppose we solve this problem with the big M method. We have already studied this big M method. So, what we do is the variables that we have introduced, the x 6 and the x 7, which are nothing but the artificial variables into the constraints, they are introduced in the objective function with a minus m factor. So, the original objective function, that is 3 x 1 minus x 2 minus x 3, in this thing we add minus m x 6 and minus m x 7, where m goes to infinity, that is m is a very large number. And this is subject to the previous conditions, the previous constraints, except that we have added the artificial variables in the second constraint as well as in the third constraint. If you recall, we need to add the artificial variables because we do not have a readily available BFS, and we need a readily available BFS to start the simplex procedure. So, therefore, we are now ready to solve this problem with the revised simplex method. Till now it is the formulation is the same. If you recall, these are the computations that have been recorded during the 4 iterations that we had performed using the simplex procedure. The first column shows the iteration number or the table number. Second column shows the basis at each of the iteration, or rather the CB, that is the basis, the coefficient of the basis in the objective function. Then the third column shows the basis is x 5, x 6 and x 7 and so on. And then the subsequent columns, they show the various coefficients that each of the variables x 1, x 2, x 3 have. In the top you will find we have the objective function coefficients, that is 3, minus 1, 0, 0, minus m and minus m. Now, these are the objective function coefficients, and then in the last column we have the right hand side, that is the value of the decision variables. Now, please look at the color coding to understand this fact that the variable x 4, for example, initially in the initial table the variable x 4 is 1 0 0. So, it is a basic variable, x 4 is a basic variable. Similarly, x 6 and x 7, they are also basic variables. X 6 is 0 1 0 and x 7 is 0 0 1. As and how the iterations proceed, and in the end we reach the table 4, 1 0 0, this column, it becomes 1 by 3 0 2 by 3. So, if you look at this particular column, the fourth column, instead of 1 0 0, it has now at the end reached to a column which is 1 by 3 0 2 by 3. Similarly, the x 6 variable, it is 0 1 0 in the initial table, and in the final table it is 2 by 3, 1 and 4 by 3. And finally the last variable, that is x 7, this is 0 0 1, and it has now in the end become minus 5 by 3, minus 2 and minus 7 by 3. So, what we find from this table is that the basic variables keep on proceeding and proceeding iteration by iteration, and in the end they come to a form which is highlighted in the blue color. Now, on the other hand, please look at the pink colored columns. What you find is that if you look backwards, that is, let us suppose if you look at the last iteration, iteration number 4, in the last iteration number 4, you find the x1 column is 1 0 0, right, and if you go back and look at this particular column, that is 1 0 0 under the x1 column, you find it is 1 minus 4 minus 2. So, starting from 1 minus 4 minus 2, we reached at 1 0 0. Similarly, x2 starting from minus 2, 1 and 0, we reached at 0 1 0, and similarly the third column, that is 1 2 1, it reaches 0 0 1. Now, my question to you is, can you try to imagine what could be the relationship between these blue entries and the pink entries? I think some of you may have observed the following fact, that is, the matrix obtained by these 3 columns in the beginning, that is at iteration number 1, and in the end, that is at iteration number 4, they are related to each other by the following fact, that is, these matrices, the 3 by 3 matrix formed, they are the inverse of each other. How is that so? Here, look at this observation. What do you find? 1 minus 4 minus 2, minus 2 1 0, 1 2 1, this matrix is nothing but the pink matrix in the beginning, in the iteration number 1, right. And similarly, the blue matrix is the second one, that is 1 by 3 0 2 by 3, 2 by 3 1 4 by 3, minus 5 by 3 minus 2 and minus 7 by 3. Now, if you multiply these two matrices, you find that it turns out to be the identity matrix. Now, this is not a chance, and this is in fact the theory behind the simplex procedure, that is, the first matrix is the other of the inverse of the second matrix. And this basic concept we are going to use in the revised simplex method, so that we can shorten the calculations of the simplex method. So, now we will see how this revised simplex method is going to work. So, let us come back to the original formulation of our problem, where we have added the slack and the surplus variables and the artificial variables, and we call each of the columns by the name P1, P2, etc. So, P1 for example is the first column, that is 1 minus 4 minus 2, P2 is minus 2 1 and 0, P3 is 1 2 1, P4 is 1 0 0, P5 is 0 minus 1 0, P6 is 0 1 0, and P7 is 0 0 1, and right hand side is 11 3 and 1. You will observe that the columns P4, P5 and P6, sorry P4, P6 and P7, these have been highlighted in the blue color to identify that these are nothing but the basic variables. So, P4 is corresponding to the basic variable x4. Similarly, P6 is corresponding to the basic variable x6. P7 is corresponding to the basic variable x7. Now, since these are the basic variables of the initial table, let us look at the matrix called capital B, which is a 3 by 3 matrix formed by these 3 columns, that is P4, P6 and P7. So, this is nothing but the identity matrix, and if you try to take the inverse of this B, you will get nothing but the identity matrix, and we can get the new B, the small b. The new small b is nothing but capital B inverse multiplied by B. So, what is this new b? New b is the right hand side, and we will record it in the table like this. So, the initial table can be written in this concise form, that is x4, x6 and x7. The right hand side is written in the last column, that is 11, 3 and 1, and B inverse is indicated in the middle. Now, we will calculate simplex multipliers. We will be denoting them by pi 1, pi 2 and pi 3. They are nothing but the product of CB multiplied by B inverse. Now, what is CB? CB is nothing but the coefficients of the basic variables in the objective function. The CB is nothing but the coefficients of the objective function in the basic variables, Now, what are the basic variables? x4, x6 and x7. So, the coefficient of the basic variable x4 in the objective function is 0. Similarly, the coefficient of the basic variable x6 in the objective function is minus m, and similarly the coefficient of x7 in the objective function is also minus m. So, therefore, CB is nothing but 0, minus m and minus m. Now, this has to be multiplied by B inverse, and this is what you get. B inverse, as I have said, initially it is the inverse of the identity matrix, which is nothing but the identity matrix itself. So, therefore, in the beginning, in the initial table, the simplex multipliers are nothing but 0, minus m and minus m. Now, we will see how these simplex multipliers can be traced out in the table of the calculations of the simplex method. Now, you will find that as before we need to calculate the deviation rows. So, therefore, the deviation rows are calculated by the formula Cj bar is equal to Cj minus pi times Pj for the non-basic variables, and in this case the non-basic variables are j is equal to 1, 2, 3 and 5. So, let us calculate these Cj's corresponding to the non-basic variables. So, x1 is a non-basic variable. So, we need to calculate C1 bar, that is the new deviation rows. So, C1 bar is nothing but C1 minus pi times P1, and the C1 is nothing but the coefficient of x1 in the objective function. So, that is nothing but 3 minus pi. Now, pi is the simplex multipliers which we have just now obtained, that is 0, minus m, minus m. Then we have the P1. P1 is nothing but the column that we have identified in the beginning, and it is nothing but 1, minus 4 and minus 2. Now, if you solve this, you multiply and then subtract from 3, you get 3 minus 6m. So, please check the calculations and try to understand how we have got this. Please note, P1 is a column vector, pi is a row vector. So, when you multiply it, you will get a scalar. Okay. So, 3 minus 0 minus m multiplied by 1 minus 4 1 minus 2. This will give you 3 minus 6m. Like this, you need to calculate C2 bar, C3 bar, C5 bar. These are to be calculated for the non-basic variables, because for the basic variables they will be 0. So, C3 bar is nothing but C2 bar is nothing but C2 minus pi times P2, which is equal to 1 minus 0 minus m multiplied by minus 2 1 0, which is nothing but m minus 1. C3 bar is equal to C3 minus pi times P3, which is equal to 1 minus 0 minus m multiplied by 1 2 1, which is nothing but 3m minus 1, and similarly C5 bar is equal to C5 minus pi times P5, which is equal to 0 minus m multiplied by 0 minus 1 0, and this turns out to be minus m. Now, these deviation rows have to be recorded in the end of that table, that is the last row of the table, and in order to find out which variable should enter the basis, we have to look at these entries and identify which one of them is the maximum. And as you can see, the maximum is nothing but 3m minus 1, which is corresponding to the third variable. So, this tells us that x3 variable is the variable which should enter into the basis. Since C3 is the most positive of the entries, therefore, x3 should enter the basis, and the pivot column is like this: P3 bar is equal to B inverse multiplied by P3. Now, here you will see that we are just picking up P3 bar, that is all. We are just picking up P3 instead of the whole thing, instead of the whole matrix, we are just picking up P3 and finding out the new P3 bar. So, B inverse is nothing but 1 0 0 0 1 0 0 0 1, and P3 is 1 to 1. So, when you multiply it, you will get the same thing. Initially it will be the same, but later on in the next iterations it will change. Then the initial table can be now completed by adding these last two columns. Now, in the last column, in the second last column, we have the entering variable, which is nothing but x3, and the pivot column. So, the pivot column is 1 to 1. This we have obtained just now by multiplying B inverse multiplied by P3. So, from the table, this is what we get. You will find that the minimum ratio test has to be applied in order to make sure which variable should leave the basis, and the minimum ratio test tells us that the minimum of 11 upon 1, 3 upon 2 and 1 upon 1 has to be taken, which is nothing but 1. Therefore, this indicates that the leaving variable is nothing but x7 and the pivot is 1. So, we apply the elementary row operations as we did in the simplex method, that is R1 is replaced by R1 minus R3, and similarly R2 is replaced by R2 minus twice R1. Sorry, R2 is replaced by R2 minus twice R3. So, the operations are the same as the simplex method. The only difference is that lesser number of computations have to be recorded in the computer memory, so that for large scale problems we can write the code and solve it with lesser computations. Therefore, this is what the table 2 looks like. Now, in the table 2 you find that the basis now is changed. The basis has become x4, x6 and x3, okay, and the rest of the things are recorded as it is, and you will find that now B inverse has become 1 0 0 0 1 0 minus 1 minus 2 1, and of course, the right hand side has become 10 1 and 1. So, this completes one iteration. Same thing is repeated for the second iteration, and the simplex multipliers are obtained as pi 1, pi 2, pi 3 using the same formula, that is CB is equal to B inverse. Now, you will note that CB has to be changed now, because the third basic variable is now x3, and the coefficient of x3 in the objective function is minus 1. So, therefore, the simplex multipliers are to be obtained using CB. So, CB is 0 minus m minus 1, and the B inverse now is 1 0 0 0 1 0 minus 1 minus 2 1, and when you multiply the two, you will get the simplex multipliers of this iteration. So, the simplex multipliers are 0 minus m 1 minus 2 m. Now, look at the new C bars, that is the deviation rows, as before as we have calculated. The new deviation entries have to be obtained for the non-basic variables. Now, what are the non-basic variables? X1 is the non-basic variable, similarly x2 is the non-basic variable. So, we need to calculate their deviation entries, and as before you know how to do that. C1 bar turns out to be 1, C2 bar turns out to be m minus 1, and C5 bar turns out to be minus m. You will note that we need not calculate C7 bar. Why? Because x7 was an artificial variable. We had introduced x7 as an artificial variable, and now it has been removed from the basis. So, we need not calculate x7 the value of C7 bar, because it is an artificial variable and it has already left the basis. So, now the entering variable becomes x2, because C2 bar is the one that is telling us that this is the most positive, and therefore, the corresponding variable x2 should enter the basis. So, as before, the pivot column has to be calculated. So, pivot column is calculated using the formula P2 bar is equal to B inverse P2, and this is obtained like this: 1 0 0 0 1 0 minus 1 minus 2 1 multiplied by minus 2 1 0, and this turns out to be minus 2 1 0, and therefore, the table 2 which we got in the beginning has to be completed by adding the last two entries, last two columns. That is, it says that because of this calculations, the entering variable is x2 and the pivot column is minus 2 1 and 0. Also, we need to perform the minimum ratio test to find out the leaving variable. So, the leaving variable is nothing but x 6 and the pivot is 1. As before, we perform the elementary row operations, and the elementary row operations tells us that this is the table 3. Now, what does the table 3 tell us? That we now have a new basis. So, this completes the second iteration. Like this, the next iteration starts. We calculate the simplex multipliers like this as before, that is CB multiplied by B inverse, which is equal to 0 minus 1 minus 1. Please note that CB is changed now because the basis has changed, and the B inverse is nothing but 1 0 0 2 1 0 minus 5 minus 2 1, which is nothing but 0 minus 1 and 1. So, at this stage the simplex multipliers are obtained as 0 minus 1 1. Again we need to calculate the deviation entries, and the deviation entries are obtained like this. So, the C1 bar is the first non basic deviation entry, it is equal to 1. Similarly, C3 is minus 1, and we find that C1 is the most positive. So, therefore, the entering variable is x1 because it is the most positive. The pivot column has to be obtained as P1 bar is equal to B inverse P1, and this is obtained as follows: 1 0 0 2 1 0 minus 5 minus 2 1 multiplied by 1 minus 4 minus 2, which is equal to 3 0 minus 2. So, we have got the new P1 bar. Table 3 is completed like this. So, that is the complete table 3. As before, we have added 2 more columns. Then we get the table 4 like this, and what do we find? We find that the right hand side is now 4 1 9, and the basic variables are nothing but x1 x2 x3. So, the BFS in the table 4 is x1 is equal to 4, x2 is equal to 1, x3 is equal to 9, and we have got the B inverse, which is indicated in this table number 4. The simplex multipliers are again obtained as follows: 3 minus 1 minus 1 multiplied by 1 by 3 0 2 by 3, 2 by 3 1 4 by 3, minus 5 by 3 minus 2 minus 7 by 3, which turns out to be 1 by 3 minus 1 by 3 and 2 by 3. And we calculate the deviation entries, and we find that all the deviation entries are negative. Now, this is an indication that the stopping criteria has been satisfied, and therefore, table 4 is the optimum solution to the problem. So, our solution, that is x1 is equal to 4, x2 is equal to 1 and x3 is equal to 9 and all others as 0, is the optimum solution to the problem. So, that is the reason why it is necessary to obtain the simplex multipliers at each iteration. And now, we are in a position to rewrite all this information that we have got in the form of a table. Now, if you look at this table, it shows the calculations iteration wise from iteration number 1 to iteration number 4. You will see the first column shows the iteration numbers, second column shows the CB, that is the coefficient of the basic variables in the objective function. The third column shows the basic variables, Then you can see the B inverse, that is at each iteration what is the B inverse. Then the next column shows the right hand side. Then the next column shows the simplex multipliers. Now you will observe that at each stage we are getting the simplex multipliers by performing the multiplication between CB multiplied by B inverse, and later on we will see how this CB inverse multiplied by B inverse, these simplex multipliers, will be the solution of the dual programming problem of the original linear programming problem. So, therefore, they are a very valuable information, and now we will like to see what are the advantages of the revised simplex method. So, the first advantage is that it needs lesser computations as compared to the simplex method, because you do not need to calculate the entire table, you just need to calculate the p bars and the simplex multipliers. Secondly, it provides simplex multipliers at each iteration which are useful for the duality theory, that is the dual problem, they are the solution of the dual problem, and also they are helpful in sensitivity analysis, which is nothing but a procedure to find out what happens if a slight change is made in the initial data of the linear programming problem. So, in our subsequent lectures we will be talking about the duality theory and the sensitivity analysis. There we will see how the simplex multipliers help us to solve the dual and also perform sensitivity analysis. In the end, I would like to give you an exercise to solve the following problem using the revised simplex method. Here is the problem: minimize x1 plus twice x2 plus x3, and this is subject to twice x1 plus x2 plus x3 less than or equal to 2, and the second constraint is 3x1 plus 4x2 plus 2x3 is greater than or equal to 16, and x1, x2 and x3 are all greater than or equal to 0. Now, there are two constraints and there are three variables. So, the hint is that you need to look at the less than and the greater than sign in order to decide what variables you have to add or subtract. So, in the first constraint we have the less than sign, that means we need to add a slack variable. In the second constraint the sign is greater than, so therefore, we need to subtract a surplus variable. So, therefore, we will not have a basic variable in the second constraint. So, you need to add an artificial variable into the second constraint in order to get a initial BFS. Once you do that, then you are ready to solve it using the revised simplex method, and at each iteration please record the simplex multipliers, so that at the end you get the simplex multipliers. Later on we will see how these simplex multipliers are useful in solving the dual. Thank you very much.